Welcome to today's webinar on decision rules. Coming to you from Morehouse Instrument Company, 1742 6th Avenue. Making sure that audio and video is working. We have a couple announcements for everybody before we start. Your time is valuable, so we appreciate you spending some time with us. With that said, okay, everything's working now, which is good. That said, I'm going to kill the camera here, load up the screen, and tell you some new things that we have. All right, so many of you may or may not know that we have this new decision rules document that's out. This is something that Greg Senker, Dilip Shaw, and several others have helped us with, but it can be found at our website. We put this out for anyone that was struggling with decision rules and trying to simplify them. If there's any interest, it's in the chat. It's Decision Rules Guidance, first edition here. You can see my screen. Download this. And basically, I cannot state this enough that this document has almost everything in it. It has formulas in it. Those that are dealing with some of the complex global risk scenarios that we're going to discuss today, they're in there. Greg has just done a phenomenal job to give everybody the VBA code in this document, and it's just instructions. If you're struggling at all with decision rules, there's a lot of excellent resources in this book. I cannot say enough about it. I'm scrolling through it pretty quickly, but yeah, here's PFA requirements, function calls, all types of different codes specifically for global risk, specific risk, things that have been kept up way too long, and I'm scrolling through, like I said, way too long behind closed doors, and like I said, right there, steps, how to calculate it all. So wanted everyone to know that really before we start, and as we get other people coming into this discussion. So with that, let's start. This is kind of a passion topic for me. It's the force of decision rules. Metrology meets Star Wars. Why Star Wars? Well, May the 4th is coming up, and I think everybody can relate to Star Wars, and it's kind of fun to talk about in relation to something that maybe somebody can relate to. So what we do, many are familiar with us, we manufacture products such as universal calibrating machines. Here, this is on the left. We have automated versions of this machine. So if you have one of our old machines, you can easily automate it with an upgrade, deadweight machines, PCMs. Really one of the main things we do. We all come to work with different purposes, but the company purpose is we create a safer world by helping companies improve their force and torque measurements. This session today is one on decision rules, not specifically with force and torque. It will be discussed a little bit because that's what we do. But this is generally if you're struggling with decision rules, hopefully this is to help you out a little bit. We offer deadweight calibrations to 0.02% of applied force, and then we go up to 10 meganewtons or 2.25 million pounds of force. So with that, let's talk a little bit. Here's my contact information. If you need it for whatever reason, wanted to get a hold of me, had a question, a simple, easy to answer question, happy to answer. If it gets more involved, then there's consulting and other things that we would generally discuss. And the general reason I show up to work is to inspire others to make better measurements. That's why, this is out of our lane a little bit for decision rules. We make them, we make conformity assessments all the time, but I'm not talking about just force or torque. And like I said, as we go over this, you're not going to see much of that in there. besides the measurement uncertainty examples. But so we have our agenda, brief discussion on measurement traceability, measurement uncertainty, and then specific risk using Star Wars and global risk using Star Wars. And the outcome, really a 50,000-foot view of this topic. It just, the outcome is so you can have that discussion and pull upon these examples and know what somebody says or what I'm talking about. If I say simple acceptance, if I say a term like specific risk, if I say a term like global risk, it's so we can all speak that same language. And then Star Wars, may the fourth be with you. Clever play on words or whatever. So looking at that, this is taken from, it's also known as business, as the hedgehog concept. In business, it's what are you deeply passionate about? What can you be the best in the world at? And what drives your economic engine? And that gives you what's called your hedgehog concept. Well, the same thing's basically said for measurement confidence. How do I know the measurements my company's making, your company's making? How do I know that they are the correct measurements? And we need to get our measurement uncertainty budgets done correctly. We need to follow the rules of metrological traceability, make sure that our uncertainties, the reference standards, and we have that documented unbroken chain of calibrations, each contributing to the measurement uncertainty. And then we have this decision risk. We need to make sure if we tell somebody something's good, that it actually is good, right? And that's how we take the measurement uncertainty into account. And the IC 17025 standard has all this in it. 651, a laboratory establish and maintain metrologic traceability of its measurement results. And then for traceability, and I already read this, but then it also says whereby metrological traceability, we want to make sure all our measurements are traceable, which is the property of a measurement result, whereby the result can be related to a reference through a documented unbroken chain of calibrations, each contributing to the measurement uncertainty. So how that works, we start at SI, not traceable to NIST, traceable to SI units for force, time, mass, length, same for torque, the two things that we do. Those are three of the 7 SI units. And then this propagates down, right? So then our NMIs, such as NIST, PTB, CNOM, all these others, they derive their traceability typically from something at the BIPM, if it's an artifact, or directly to the SI. And then from there, we go primary calibration laboratories, reference laboratories, and so on. But the big point here is that measurement uncertainty data is cumulative from one level to the next level of the hierarchy, which means if you come to Morehouse and the best we can do is 0.17, because we're a primary laboratory, your uncertainties cannot be better than that. They can only be worse. And that's the documented unbroken chain of calibrations. The reference is very significant in that aspect. So when you shop on cost, maybe the labs with the primary standards are more expensive than the lab that's general calibration. And it's very important to realize that early on, because what we're going to talk about today all relates to these uncertainties. And then we get into other things like definitions. So anybody ever been to a presentation? They talk and they start talking in anagrams, right? Or like things like SPC, GR, PFA, and unconditional PFA, PFR, FA, FAR, FRR, and all of a sudden you're completely lost and have no idea what people are talking about. Well, I think it's good to define things, and these are just general ILAC definitions, and we have something like a tolerance limit, right? That would be right here, our tolerance limit specified upper or lower bounds. So we have a device, let's say a force gauge, that's plus or minus 5 pounds. 500-pound force gauge plus or minus 5 pounds. So the lower tolerance would then be 495, and the upper tolerance would be 505. We have an acceptance limit, specified upper or lower bound of permissible measured quantity values. So typically, we're going to set that it's going to be apply some guard band, some percentage of measurement uncertainty. We can use global risk, specific risk, not there yet, but we're going to do something as far as our acceptance limits go. Typically, unless we have a guard band equal to 0, then it'd be the same as the tolerance. But we'll talk about that. We have a measured value. That's the quantity value representing a measurement result. So our measurement here, I drew another line for that measured value. If that's between the acceptance limits and we calculate our risk properly, we will issue a what? We will issue a pass. And then what the guard band is basically the difference between the tolerance limit and the corresponding acceptance limit defined by some criteria. And our decision rule describes how measurement uncertainty is accounted for when stating conformity with a specified requirement. That's a rule. We're going to figure that out. What is that rule? Do you have the rule? Do you know the rule? Things that we need to discuss. So measurement uncertainty and specifications. I like this slide a lot. That's why it's here. So every measurement always has a margin of doubt. Many people have probably heard uncertainty. What do you think about uncertainty? Doubt. Doubt the validity of the results. We think we know our measurement when we apply our dead weights to 0.002% of applied. We think we know it's that good. There is some doubt. We don't know that if we apply 10,000 pounds, we don't know that it's exactly 10,000 pounds, but we think we've done our uncertainties well enough that we know it within plus or minus 0.002% of applied, or 20 parts per million, and then we add this unit under test and what it contributes to it. So anything has, even back to the SI, there's some doubt, there's some unknown. Uncertainty is inherent limitation of the measurement process due to instrumentation and process variation. And then measurement uncertainty, really important part here, it does not include mistakes. So if I have this high bias, or if I fail to calculate my measurement uncertainty correctly, something or another, I might not capture it. And a technician makes an error, right? Put something in the machine, doesn't align it properly. That is a mistake. It will transfer to the unit, and it does not include it. So I typically call mistakes typically on the process technician. Hopefully you've captured all of your error in this, but I also find a lot of mistakes when I work with people in their budgets. So that's there as well. But if we look at a budget, what should a budget contain? And A2LA has this document, R205, and these come from section 6.7.1 of that R205 document. They're also found in the GUM. I think these are real clean to say, hey, this is at a minimum, documentation consideration shall be made for the following. There's usually a lot more to uncertainty budgets than these, but this is an absolute minimum to look at. Do I have repeatability? Do I have resolution of the, of the device? Do I have reproducibility of my technicians, of my process, of my machines? Do I have the reference standard uncertainty? Do I have that stability that people like to leave out all the time? Does it drift from one calibration to the next? Have I captured the environmental factors properly and what that does to my measurement? There's a lot in there. This one's just an overview, and then 17025 section 6.7.6.1. It says when evaluating measurement uncertainty, all contributions that are of significance, including those arising from sampling, shall be taken into account using appropriate methods of analysis. We could spend the whole week talking about just that sentence alone. So ideally, what does this mean? Let's wrap it up. We do a calibration on a 10,000 pound load cell. We do plug in all the contributors that we think we've for our uncertainty. We have our reference standard right here. This is the reference used to calibrate that load cell. And then we have all these other conditions. ASTM lower limit factor, the statistical estimate of error. It's really reproducibility of the device in our equipment, expected performance at the time of cal, all these other things. And at the end, we look at this budget and we say, all right, I sent this 10,000 pound load cell to Morehouse. their reference standard, when I run my full budget, contributes 14.43%. Now, remember I said if you send it to another laboratory. Well, another laboratory uh, does the same cal, we're assuming everything is virtually the same. They're further down on that hierarchy, and their contribution to the uncertainty could be higher. In this case, it was 95.74%. So if I'm the lab and I want to lower my overall uncertainty, probably need a different calibration provider if I'm going with further tiers down on that hierarchy. Maybe I move up a tier. Maybe I move up 2 tiers. It's all dependent. And you're going to use this information. This uncertainty is crucial because you're going to use this to make that conformity assessment. So in this same situation, something walks out the door here, I'd say expanded uncertainty, but this is really expected performance of the device if used under similar conditions. Walks out of Morehouse at 0.41 pounds, walks out of somewhere else just because the reference standard uncertainty is a lot higher at 4.03 pounds. Different expanded uncertainty using primary standards is approximately 10 times lower than using secondary standards. So just more considerations. We get into decision rules. We get into that third important piece here, and that says when a statement of conformity, IEC 17025, statement of conformity to a specification or standard is provided, the laboratory shall document the decision rule employed, taking into account the level of risk such as false accept and false reject and statistical assumptions associated with the decision rule employed, and apply the decision rule. So what is that, right? What are we doing? What does that look like? Graphically, here's something that I just worked up. It's our 10,000 pound device, specifications plus or minus 10 pounds. So we have an upper tolerance. Remember our specification limits the tolerance of 10,010, lower tolerance of 9,990. Measurement uncertainty in this case is 1 pound. And then there's a graph. And what we're really looking at is this measured value at 10,008. And when we look at what risk or evaluation of risk, we're looking at, we draw this tail based on the measurement uncertainty, and then we figure out how much of that normal distribution or Gaussian distribution is outside or inside. Right here, we have a little bit that's outside, and the answer here outside is 2.275%. Most people, if they're working with Z540.3 method 5, that is a decision rule. It wants you to limit your risk to less than 2.275. So customer sends us a device and they say, please calibrate as found, manufacturer 10,000 Newton load cell, serial number with manufacturer readout, in compression only, and issue a pass when the PFA using specific risk is less than or equal to 2.5, otherwise fail. They send us this, we plot we put all these numbers in, we say, okay, they're asking for risk that's less than 2.5%. We calculated 2.275% is over the tolerance line. Therefore, we issue a pass and everything is good. So, got into a little bit of specific risk there, and there are 2 general types of risk associated with conformity decision. Consumer risk, the probability that a non-conforming item is accepted, and this is where things get really fun really quickly, right? This is also known as type 2 error, pass error, false accept risk, and probability of false acceptance. No, we can't just say it's one thing, right? Today, we're specifically going to talk more about PFA, which is probability of false accept. But if somebody says these other terms, I put them in there so you would know them. And then we have producer risk, the probability that a conforming item is rejected, also known as type 1, fail error, false accept, false reject risk, and probability of false reject. So the easiest thing I can say here is if we're looking at what this means, consumer risk can have potential adverse impacts to a product system performance, and producer risk directly impacts the cost of manufacturing, testing, and calibration. I love this slide from NAVC. It's really what we're getting at. We want to avoid these things, the bad items, right? False accept means, hey, we shoot a missile, it doesn't land where we want it to land or doesn't make it to its target. False reject, that is unnecessary rework. So over here, this is our PFA, right? This is saying something, we said something is good when it's actually bad. And on false reject here, this is our PFR. We said something is bad when it's actually good. So we did rework. And if you think about in your organization, how much waste, if you're into lean and the other stuff, Muda, how much waste is produced by people not knowing if their measurements are good or bad. How much rework. I calibrated something, technicians started using it, we produced a bunch of product, and all that product now, somebody said it was all bad, so we remeasured all of it, and it really wasn't bad. But we had to measure it. Or there's stories, lots of stories, where, oh, just measure it till it's good. Is that a acceptable method? Of course not. So where we really want to be is on that good side, where we're making the correct decision and reworking stuff we need to rework, and we need to be on that accept side where we know that if we say something's good, it's going to hit the target. So back into specific risk. Specific is also called bench level risk. It's based on a specific measurement result. May be characterized by one or two probability distributions depending on the method. And then any representation with only one probability distribution is always a specific risk method. Okay, that's what we're talking about when we say specific. I drew it on that 10,000 Newton force gauge example. We're drawing it again. Here we have a measurement result with specific risk. We have our tolerance limits, and a lot of the curve is over the tolerance limit. Then we get into global risk. And global, also called process level risk, it's based on a future measurement result. It is used to ensure the acceptability of a documented measurement process based on expected or historical information and usually characterized by two probability distributions. So if we think about something real simple, Steph Curry, or let's go Caitlin Clark. For those who don't know, Caitlin Clark's a phenom. She shoots three-pointers all day long. But let's say Caitlin's taking a three-point shot. That one shot, instantaneous shot, is a specific risk. It's either going in the basket or it's not, right? If too much is hanging over, it doesn't go in. If just enough is right on, the shot's accurate, it goes in. Global risk is a little different. Global risk is saying, okay, Caitlin's made 97 out of 100 three-pointer shots, right? And she shoots one and it doesn't go in. And global risk says, well, since she made 97, we're using this historical information and we're saying, hey, it should go in. We're going to move this value over. And it gets a little bit confusing when you think about this and how it is, but it's a lot of probability and statistics, and we'll cover that more in our Star Wars examples. Other things you need to know, consumer risk, also PFA, it can be altered by tools like controlling measurement reliability, calibration intervals. Hey, if I have things that are constantly failing calibration, one thing I can do is look at my interval analysis. Maybe I put it out too long. If I have things that are always passing, maybe the 6-month interval that I have could go to 9 months. Calibration process uncertainty, calibration adjustment, guard bands. These are all things, and we're going to talk about guard bands right here, because the term guard band, what is this? It appears to have its origin in the early radio days when a band of frequencies expected to be utilized by 2 radio channels or stations were separated by a band of frequency that served to guard against mutual interference. You did not want to be driving down the road if there was not enough of a guard band and you're listening to Led Zeppelin and have Johnny Cash, the country, or Waylon Jennings or something blending in with that. So they put a band to say, all right, in this area, if I tune to 98.5, the next channel is going to be 98.1. And that anything in between, we're not going to have any channels in between, and we shouldn't have interference with people's radios. So pretty easy concept, but we also can apply this to measurement. And when I said that first scenario with the load cell, when Morehouse did the calibration, that's really what we're looking at. We have a lower measurement uncertainty with that device, and that lower measurement uncertainty translates into a much larger acceptance interval in which we can say the device is intolerant or a smaller guard band. When we have that larger uncertainty, when the other lab did the calibration, that translates into a smaller acceptance interval. So specific risk, both global and specific, measurement uncertainty of the reference is included in these calculations. Some people start with TURs and all that stuff, but just know the smaller my uncertainty, the larger my acceptance interval, and the larger my uncertainty, the smaller my acceptance limit. ASME, really great document here. B89 7.4 describes both risk levels well. Specific risk mitigation can be thought of controlling the quality of the workpieces. Single shot, is it going in? I practice, I can keep getting sharp. Well, program levels are described as controlling the average quality of workpieces. So I took 100 shots, made 97, 90, pretty easy math. 97% of the time we're making something, but people wouldn't, not the 3% reject if you're making product could be a huge problem, especially if you're making airplanes, right? Hey, 97% chance that the engine's good. Would you get in the plane if there's 3% chance if it's bad? No. So we got to weigh these risks with all types of different scenarios. Specific risk, I really like ASME on here, is being an instantaneous liability at the time of measurement. We are measuring something, we're applying a force, a torque, or whatever we're doing, we're applying it to it, we're reading what the instrument says. Customer has supplied us with pass-fail criteria, and we're saying, is it good or bad immediately, right? Did I make the basket? Did I not make the basket? Yes, no, we know. And then the program is more based on historical data. So specific risk is also called bench level risk, and it's based on that instantaneous liability. Triggers a response based on data gathered at the time of test, characterized by 1 or 2 probability distributions depending on the method, and any representation with only one distribution is specific risk. Really want to hammer that point in. That's why it appears twice. Statement of conformity, when we're saying something, did it pass, fail? Did the basket go in? Did it not go in? There's really, really 2 possible outcomes, right? Did it go in? Did it not go in? Is it conforming within the specification, or is it not conforming within the specification? Here, first Star Wars reference here. A looks like a TIE fighter a little bit. We shrink our uncertainty, it probably look completely like a TIE fighter. And maybe B's a Y-wing or something like that, a longer ship. But in the B situation, the measured value is inside. It's just our uncertainty is so large that there's a large percentage chance that we're saying something's good when it's not. And then ILAC G8 goes into these different criteria where you say, hey, all right, uncertainty bands and specification limits, just another way to draw these things. These 2 scenarios pass, well within, pass. Here, maybe a third, quarter or a third's out. That's a fail, and that's a fail. So when we say only 2% risk, what we're saying is only 2% can be over one of these lines. So we would say it's a pass if we draw that out and are out of that whole band, that only 2% goes over the acceptance line. We also have these non-binary statements. I'm prefer, my opinions on things very biased of working in the field for 25 plus years. I like this scenario. I do not like indeterminate pass or indeterminate fail. These are things that you're just going to hear me talk about. We're not going to have a slide, but why I like this one is a lot of times people won't tell you what when to pass something and when to fail it. They're just going to say, all right, make a calibration and we want a conformity assessment, do with whatever you want. In this scenario, this was in UCAS LAB 48. I have measurements that pass, and then I have this window of possible pass, and anything above the tolerance limit is a fail. Reason I like this is because someone might be okay with 5% risk. They might be okay with 2.5% risk. They might be okay with 3% risk. If they do not tell us that, then how do we know if we can pass or fail? All we know is that they're not okay if it goes over the tolerance limit. And if they were okay with that, they should have really increased their tolerance limit. So ASME 2001 has this, I always like this picture, this graph in here. It's just saying things a little bit differently instead of calling things like a stringent acceptance zone, right? That is our guard banded and the relaxed acceptance zone. And then they talk about rejection zones. And for those that are in manufacturing, this makes a lot more sense than some of the terms we talk about in metrology. This is adopted from ISO 14253, and it's just another representation that says, hey, the smaller your uncertainty, the larger your conformance zone, and the larger your uncertainty, the smaller the conformance zone. Just another way to draw that and correlate it with the metrological traceability pyramid. As the uncertainties keep getting larger and larger, there's less room and less room depending on your device. Now, this is one, when people say I applied a guard band of W equals 0 or I applied no guard band, what that means is it's simple acceptance. That means that someone could still issue you a pass as long as the measurement is at the tolerance of the device. Here we have a resistor example. This is in JCGM 106. And at that line, the probability of conformance and the probability of non-conformance is each equal to 50%. So 50% of our distribution is over the upper specification limit. That's what they're saying when they do simple acceptance. If you own that equipment and I'm allowed to provide simple acceptance to you, I can pass as much as 50% of the risk. Certainly something you don't want if you say, well, we're measuring the amount of arsenic in something, and if we determine that any more than 2% of arsenic in this mixture can kill you, and I'm going to give you a result that has up to 50% arsenic, you do not want it, right? I am very biased on this. I think simple acceptance does not serve any purpose in metrology. I think the standard is very clear that you have to account for measurement uncertainty. And by accounting for measurement uncertainty, by ignoring it, is not accounting for it. So let's have some fun with Star Wars stuff. The Death Star exhaust port. Our rebel fleet is quickly gathering after receiving the Death Star plans, in which we've uncovered that a torpedo can be fired into a 2-meter exhaust port vent, which would impact the core and trigger a catastrophic explosion. We know from Rogue One that they got these plans. The Empire doesn't think that this vent port is a problem. Someone had built this design flaw into it just in case the Empire got too strong. And we know that our proton torpedo measures 0.5 meters, and we can send X-wings in there that if we devise the right plan, we can take the shot, make it, and destroy this world-destroying moon, planet, ship, whatever you want to call it. How do we put this all together? Well, our proton torpedoes are a half meter. So when we start saying things like a TUR of 4-to-1, we have a 2-meter hole, a half-meter proton torpedo. What is that? Divide 2 by 0.5, that's 4. So when we discuss terms like test uncertainty, we are saying the measurement uncertainty is 4 times less than the tolerance, or the tolerance is 4 times more than the measurement uncertainty. ILAC G8 defines TUR as the ratio of span to tolerance to a measurement quantity subject to the calibration to twice the 95% expanded uncertainty of the measurement process used for calibration. This is where we get things, additional things like terms like 2 sigma means I can fit 2 standard deviations, and 4 sigma can be demonstrated using this concept. You can see that down here. There's 2 sigma and 4 sigmas taking up everything, and the 4 torpedoes are in there. So what that means, 2 sigma means that 95.45% of the population lies within 2 standard deviations of the mean. That population is represented above. 2 standard deviations would fit approximately those 2 proton torpedoes. So if we went the other way with this, we could say like a TUR of 2-to-1. We could not use higher than 2 sigma in this case, and only 2 torpedoes would fit between our specification limits. Most commercial labs typically offer some type of coverage factor. You've most likely seen it. K equals 2. Well, K equals 2 corresponds to 95.45% confidence. And that's what we're going to use in our example here. We can calculate, we want to make sure that our Rebel fleet, if we take the shot, we want to calculate our guard band multiplier on here. There's a lot of information out there on doing this. That decision rules book that I put in the link, it's a simple formula. The formulas are right here as well. The formula in Excel, really easy to implement, is a norm inverse function, and you divide that by 2. When we use this number, we can calculate our upper and lower acceptance limit for this, and we're basically saying with 95.45% measurement uncertainty, allowing for that 4.555% risk, that we need to take a shot between the plus or minus 1, and that shot needs to go in between these 2 numbers, and these 2 numbers represented here by this graph. Our vent port, we've calculated this. Specifically, we've calculated that guard band using the previous slide. And if you're wondering, yes, we will make the slides available, but you can get all of this in that decision rules guidance booklet. So that's it. We want to sink the shot. We want to destroy the Death Star. We know our measurement uncertainty. We can calculate that pretty easily by looking at our proton torpedo. We can say, hey, it measures 0.5. I need half of that to go in the hole, so just a quick analysis, 0.125. We're saying the maximum allowable risk is 2.5%. That's what we're good with. That's probability of conformance. Calculated everything out, and we have our acceptance limit, and we have our tolerance limits. We have the vent port. All is good if that shot is between negative 0.7550 and plus 0.7550. Now, what if Luke or somebody else, one of our other squadron, what if they take that shot and it doesn't hit within these points? What if that measured value, because here we have a measured value of 0, what if they miss? Now, under specific risk, basically says the measured value here, all we did was move this measured value to 0.99. And how much probability, how much of our torpedo is outside of that hole? If we're shooting baskets, how much of our basket is outside? And it's calculating that probability of non-conformance is 46.812. That's how much is over the side of our tolerance limit. 46.812%. What do you think is going to happen when we're shooting a torpedo? Not going to go in, right? It's going to hit the side. It's going to blow. Maybe some damage, but not going to easily go in. our probability of conformance, inverse of that, is 53.18. So if we were making a measurement, the risk that we would tell a customer that they would have on their device, we would say this device there's a 46.812% chance that this device is non-conforming. And there's a 53.188 chance that it is. And most people are going to fail that measurement. So those that have watched Star Wars, spoiler alert, we know Luke makes the shot. He was awesome. And the Death Star's destroyed. Our heroes celebrate. There's ribbons given out by Princess Leia. And the Rebel fleet is joyous. So if this were global risk, hopefully that concept is in somebody's head. You very much visualize it. If the shot measured 0.99, there was a 46.182% chance the shot would not go in. However, this knowledge or curve suggests by using our law of averages that the shot has a 99.11% chance of going in. And people are like, say what now? You just showed me it's not going in. Well, that's specific risk. It's an instantaneous liability. But based on Luke, and we know he took all these shots at Womp Rats back when he was on Tatooine, right? He knew he could shoot a shot down that hole. He's made several when he was a kid and everything else, his land speeders and other stuff. All he did was shoot Womp Rats, and he would hit them very easily. So now we take that law of averages and we say, yeah, well, under specific it fails, but under global, since we're using a lot of measurements, and Luke had shot 100, he made 99 out of 100 Womp Rats or whatever. So we're no longer controlling individual work pieces. We are controlling the average quality of all the work pieces. And to control that average quality, we need to have the data. There's this awesome program. This is a screenshot from it. It's called SunCal. It's by Sandia. You can get it. You just type SunCal software Sandia. You can pull it, play with it. There's a little bit of a learning curve, but you can put all these numbers in there. And this basically says, hey, my specific measurement risk, TUR is 4-to-1. You hear these magic numbers. TUR usually used for just global risk, right? But it can be used for specific as well. It just gives you a quick ratio. Measured value, specific risk, as we said, 46%. Well, globally, since we have all these numbers and we have the high TUR here, globally, this is saying, hey, Luke takes the shot, even though we measured it at 0.99, it's basically saying that our PFA, probability of false accept, is 0.79%. So there is a very, very high percentage chance that is going in as stated before. So vent port, process risk, everything else, it's using those averages, often using integrals, very complex math. We get away from super easy math into complex math when we go to global. And that's all the more reason that our decision rules with the VBA code people can implement. So Star Wars global risk based on that future measurement result used to ensure the acceptability of documented measurement process. It's based on the expected or historical information as usually categorized by two probability distributions. If we look at the same, X-Wing is not much different from the T-16 Skyhopper that used to blast Womp Rats. So that's it. That's how global works. You need to have other things like end of period reliability analysis. This is a whole nother, maybe there's a separate webinar another day on this. There's a lot of stuff on end of period reliability, calculating confidence limits. In simplistic terms, we basically say it's the number of intolerance results divided by the total number of calibrations. And reliability decreases with time after calibration. Something we need to determine is how much testing is required to demonstrate reliability with confidence. Can we use the Skyhopper and an X-Wing together? Can we lump in similar model numbers? Or do we need to have the exact same model numbers? Can we use the post-dating? in our analysis? Does everything have to have the same calibration interval? It requires a lot of prior knowledge of those measurements. Like I said, basketballs, Caitlin Clark, she makes 97 out of 100 3-pointers. There's a high probability that the next shot she takes is going in. So there's a simple formula that tells you for end of period reliability, sample size right here, real easy. We can plug that one into Excel. You can copy and paste it into Excel. You type it into Excel now. Basically going to say, if we want a 95% end of period reliability at a 95% confidence interval, that we need 58 point some samples, and you're going to round that up because there's no 58 and change. It means we need 59 samples with 0 failures. Thus, if Luke successfully targeted 59 Womp Rats out of 59 shots, we would now have our reliability data and could start using these global risk models. If Caitlin Clark, basketball, makes 59 out of 59 3-pointers, then you can say, hey, there's a good chance that that next one is really going in, right? And our risk of not making it is really quite low. And that's all this is wrapped up in. It's a strange topic when you think about it, because you think about spatially that torpedo is not going in, but based on the law of averages, it's saying, yeah, nope. We have that other curve, so we know even though it's in the instantaneous liability is saying no, on a global scale, we're saying yes. End of period reliability. I encourage people to seek out this paper. This is by Paul Reese and John Harvin. It's called Risk Mitigation Strategies for Compliance Testing. And EOPR assumes a worst case TUR here in this picture. When both true EOPR and TUR are low, most measurements lie outside of the tolerance, and the risk of falsely accepting an item is low. The false accept drift is low when ERPR is high, near 100%. So it's basically saying if you can meet this true EOPR of better than 95%, your false accept risk is going to be rather low, and this graph is showing that. And then there's another one. I love sticking this in here because everybody always harps on this 4-to-1 TUR. That's origins are from 1950s, Jerry Hayes, Navy days. Lots of work on test accuracy ratios and some other by Wisen and Clark and some Grubbs, Kuhn, some other really awesome people in the 50s. But Jerry Hayes with the Navy really came up with a 4-to-1. They were plotting these curves, and it really they were thinking that we needed 3-to-1, and then we're not comfortable enough and made it 4-to-1, and that's stuck. And there's some really good math behind it. But what Paul Reese and John Harvin did is they wrote this paper that basically said, hey, that true ratio is 4.6-to-1, and it's the managed guard band is based on the fact that for a given measurement capability index, that's TUR. That's in JCGM 106. TUR is often called measurement capability index. There's a maximum consumer risk for all product processes. You know, you may notice peculiar behavior in this region where you're like over here, and this paper really goes into great detail with this. But the PFA drops because when you get a TUR of less than 1-to-1, the difference between the reference standard and the M&T is the same, accuracy-wise. The problem of falsely accepting products drops off significantly. Because nearly everything is like falsely rejected. I mean, you don't have your TURs under any control, and you really don't know what's going on. Your measurements are all over the place, and therefore, when it gets super, super low in this region after it meets the peak, you don't know what you're doing, basically. So another Star Wars example. We want to build an army of clones. So this is global. This is where global really shines in manufacturing. Optimal height of our clones is 70 inches, plus or minus 2 inches to fit our clones with the same gear and maximizing cloning efficiencies. Our measurement system has a test uncertainty ratio, also measurement capability index, of 8.1, meaning our calibration process uncertainty is 0.25 inches. The question becomes, what is the probability of saying a clone conforms to the specification when it does not? there's some cool things going on here. 8 to 1, that's a great TUR. That might be something like, hey, people often buy the wrong equipment and then they get these low TURs and they reject a lot of product. So I'm really, my measurement process is such that my measurement capability is 8 times that of what I'm measuring. So let's look at that. Let's put this into SunCal and see what this tells us. Well, this tells us over here our global risk total PFA is 0.0039% or 3.9 per million are expected to be said to be in conformance when they are not. So that TUR of 8 to 1 is basically saying, hey, 3.9 per million. So that means virtually 1 out of every 5,000 will be too short. So, and the inverse of that translates to about 1 out of every 5,000 being too tall. And the movie New Hope certainly demonstrates that when the stormtrooper hits their head as they were taller than their counterparts. So, shifting the focus more towards design, particularly regarding the headgear, recalls the importance of Luke's experience when he dons. Some will remember this when he dons that stormtrooper hat and explains, "I can't see a thing." It underscores the need to concentrate on essential aspects when designing and testing models based on risk assessments. So, if anybody was curious why the stormtroopers never hit our heroes, it's because of that comment, the Empire design gear in which people could not see out of. And even though they designed it based on our models, which were hypothetical, where only 1 out of every 500,000 was too tall, um, uh, they had a serious design flaw in being able to see. So if you invest heavily in building an army of clones, but equip them with armor that impairs their vision, can we realistically, if we were the Empire, expect to rule the galaxy? And people do this all the time. They don't understand what they're making and how they're making it, or what they're measuring. So, it sounds like basic, but these oversights occur all the time. There's numerous examples you can look up. You can look up facial recognition software where it thought certain ethnicities all look the same. You can look up hand drying um, uh, machines that when you go to the laboratory, that if you had certain color skin, that the device wouldn't turn on instead of just using sensors. They make these oversights all the time, and then they get out, and it's a bad reputation for several companies. But so global versus specific risk summary. Hopefully you found the Star Wars or took something away from those Star Wars examples. A specific risk is dependent on a single probability function and can be referred to as a probability of conformance from the customer's point of view. Global risk, kept hammering that one, depended on two probabilities, the second one being a priori knowledge, which could be taken as a process or instrument reliability. And typically, I did mention this when we were talking TUR, we were talking about global risk, so it can be used can also be used as a ratio for bench level. Like the example that I used with the 0.755, our acceptance limits of negative 0.755 and plus 0.755. I know if I have a TUR 4 to 1 and I was looking at that scenario, you could calculate that out. And that's pretty easy to do. Things we can do to control or mitigate our risk. We can buy better standards or send our equipment to labs with lower measurement uncertainties. Other things we can do, hey, if we don't, we hear this all the time. Well, calibrate to manufacturer's tolerance. Well, do you need it? How did the manufacturer come up with their tolerance? Was it one day they were standing on one leg and someone achieved once but never repeated it? Don't know, right? But if you don't need it, your equipment, and you want to do reliability studies and everything else, there's no reason. If you need 0.2%, there's no reason to hold the lab to 0.1%. We can decrease the time intervals between calibrations. right? I mean, stability is a big thing. We calibrate meters for customers. We usually use a load cell simulator. That's what we do, and that has a calibration for. If we only calibrated that annually, wouldn't be good enough. We need to calibrate it at a minimum quarterly to get the specifications and provide the lowest measurement uncertainties, which we deem reasonable. Because if we go to monthly, it doesn't get much better. So we found that optimal interval for the high-end simulator that we have is about every 90 days. Some people may calibrate, more frequently than that. Maybe they calibrate their meters daily if they have like awesome equipment, and they can use the 24-hour transfer specs. Maybe they use the 30-day specs. All kinds of different things that can be done. Maybe it's a matter of two-course resolution where somebody bought something, a cheap indicator with a good load cell, and just a matter of improving that resolution can lower that overall process uncertainty. So some things, calculating measurement uncertainty correctly is essential to everything that comes after it, including decision rules. Traceability relies on a documented, unbroken chain of contributions, each contributing to the measurement uncertainty, linking them to the appropriate reference. And specific and global risk use different strategies, as one deals with specific measured value, while the other one typically uses average data and TUR reliability targets. Like I said, I hope everybody found this useful. In the chat window, you can download our document, which I started this presentation with, on decision rules. There's a lot of information. Some of the stuff that we covered today is in there. There's a lot more than what was covered. There's a paper in Quality Magazine if you want to read it, the Star Wars of Decision Rules. That's what this webinar today was based on. Those examples are in there. Describe them a lot better than I did today because I go into the utmost detail. Today's goal was probably a 25,000 foot view. I would say 50,000, but we went a little bit deeper. I had a couple slides in there on how to calculate specific risk and showed some other a little bit more advanced topics as well. So hopefully those that know something about decision rules got more out of it, and hopefully those that were confused on global versus specific got some additional things, and now you can at least explain that, hey, global's got that 2 distribution curves, and specific you typically only has 1, and specific is an instantaneous liability where global is based on average data. There's other recommended reading. Here we have UCAS LAB, Decision Rules and Statements of Conformity, is highlighted. I really like that document. I think it does a great job. These other documents like JCGM 106 is a bit difficult to deal with. If you haven't picked it up, the Metrology Handbook 3rd edition, Chapter 30 specifically, if you have that, you can go look at that. That's more on bench level risk or specific risk, talks a lot about simple acceptance. And there's all these other documents down there. Some cost, some are free. And then a lot of these papers, there's links here. Our latest article on quality, the definition of fool is drowning man who tries to keep it a secret. That's an article on quality about purchasing the wrong equipment. And then there's the force of decision rules, unraveling the Tom Brady Deflategate, which Introduction to Statistics and Metrology, and another excellent book, does a great job of in that. And Greg and I took it a little bit further than Colin and everybody did, but that is one. If you are struggling at all with measurement uncertainty or statistics, I highly, highly recommend Introduction to Statistics and Metrology, written by some great people out at Sandia. With that, we have YouTube videos, we have free downloads, spreadsheet calculators. We've just updated our CMC, calibration and measurement capability spreadsheet. We are looking for more followers on LinkedIn. We're close to 4,000, and we would love to get to 4,000. We post a lot on LinkedIn. If you want to know what's going on, new blogs, new articles, 2 new blogs that are coming out, one on resolution and the other one on specific force measuring instruments, which does not get a lot of coverage. In fact, you can Google specific force measuring instruments right now, and you probably won't find much of anything. That was some people use those types of insert loop rings, other rings, analog gauges, and such for hardness tests and whatnot. So there's going to be a good blog on that coming up. There's also, watch out, there's our internal company. They get an email. All of our team members get emails Tuesday through Thursday that has each of those emails deals with a metrology topic specifically related to force or torque. There's about 112 of those emails total. And if you watch out, we're going to be opening that up to the public as well. It takes about 10 minutes a day. But if you want to refresh your knowledge on force, torque, decision rules, metrological concepts, some statistics, some uncertainty analysis, watch out for that. With that said, if anybody has any questions, I'm happy to answer them. Just please type them in the chat. If you do not, I would just say, hey, thank you. Your time is valuable. It's highly appreciated that you spent it with us. And enjoy the rest of your day, East Coast, West Coast, overseas, or whenever. Hopefully specifically this time that we presented, it's a little bit different from what we have been doing, worked for your schedule. And so with that, again, thank you, everyone. I'll stay on for a couple minutes and see if questions come in.